11th. We're going to continue on today in our look at Unit 3, Quantities in Chemical Reactions. We're going to be moving on to some new calculations that we haven't gone through yet for empirical and molecular formulas. Just gentle reminder, take a look at my office hours. I'm available then most easily. Not a ton of you have been emailing me during office hours, but it's a great opportunity. I'm sitting by my computer waiting to see if any of you need any help with anything. So it's a great way to get any help. And if some of your peers have posted questions, I'm also posting the answers to their questions in that FAQ document. So even before you email me, you may just want to take a look on that link to see if someone else has already asked for, say, a solution to a homework problem that you may be having trouble with, because it may already be there. Okay, but again, I'm here to help. Feel free to reach out. That's what we're doing to try to get us through this next unit. Okay, the content we're going to be looking at today is in your textbook, section 6.7 to 6.9. It's on page 289 to 300 of your textbook. Okay. So we're going to learn today about two things called empirical and molecular formulas. Then we're going to do some practice problems together, and then I'll give you some practice problems that you can work on tonight to finish up your hour. This should take about half an hour to go through this portion, and that gives you about half an hour to practice those practice problems. And those are what you'll submit to me on Google Classroom under your assignment for week 2, activity 2. Okay. So what we should be able to do today by the end of the class is students should be able to calculate empirical formulas when given the percent composition of a sample. You could also be asked to calculate the percent composition of a sample, because we know last day we learned how to do that. And you should be able to calculate the molecular formula when given the percent composition and molecular mass of a sample. Okay. So at the end of the class today, you should be comfortable doing those two things. Okay, quick background on what an empirical formula is. Now, an empirical formula is something that's derived exclusively from experimental observation. It's not something that's derived from theory. Okay, so essentially what the empirical formula tells us is it tells us the simplest ratios that elements combine in. Okay, so it tells us for every one of these atoms, how many of another atom are you going to have. It doesn't actually tell you the exact quantities, but it tells you the simplest ratios. Is it a 2 to 1? Is it a 3 to 1? Is it a 5 to 2? It'll tell you the simplest ratios. So here's what I mean. Ethene and benzene, the true molecular formulas of ethene and benzene, ethene is C2H2. We can see that right there. That's what we would actually write as the true empirical formula of that compound. Benzene, on the other hand, has a chemical formula of C6H6. Okay, so those are their true molecular formulas. Okay, that's the actual quantities in which those two atoms combine. We need 2 carbons and 2 hydrogens to make ethene. We need 6 carbons and we need 6 hydrogens to make benzene. Now, their empirical formula, though, remember, just tells you the ratio. So both of these compounds, for every 1 carbon, have 1 hydrogen, right? If you simplify 2 and 2, that ratio is a 1 to 1. So for every 1 carbon, we have 1 hydrogen. It's 2 and 2. Same thing here with benzene. If you reduce 6 and 6, you're going to get 1 and 1. So that's the same thing. It's telling us for every 1 carbon, we also have 1 hydrogen. So the empirical formula, remember, is just telling us the ratios. Okay, so ethene and benzene would have the same empirical formula. They have the same ratio of carbon to hydrogen, even though they have different molecular formulas, C2H2 and C6H6. Okay, what we can see too is there can be elements that have the same empirical formula that don't have similar characteristics. So we can see, for example, ethene is a flammable gas, whereas benzene is a liquid. We can say they have very different melting points, -81 to 5.5 degrees Celsius. Very different boiling points, different densities. And what they're soluble in is also, some of the things are different, okay? So just because they have the same empirical formula doesn't necessarily mean they have any of the same properties. It just means that they have the same ratio of elements. Okay, so let's take a look. I'm going to make myself disappear here so that we can do the calculations together. We're going to say, if these are our given molecular formulas, what would our empirical formulas be? Now, we have a 6 here. Whoops, let's go back. We have a 6 here and we have a 6 here. So if we reduce 6 and 6, the empirical formula is going to be CH, okay? Both 6 and 6 are divisible by 6. Okay, so we're going to reduce that down to 1 and 1. What that's telling me is for every 1 carbon in this molecule, there is also 1 hydrogen. That's the simplest ratio. Okay. Okay. If we look at something like C8, H18, okay? So what's a number that both 8 and 18 are divisible by? Well, that's 2, right? We could reduce this. Our empirical formula then would be C4H9. We can't reduce 4 and 9. There's no common factors of 4 and 9 there. So this ratio is telling me for every 4 carbons, there's 9 hydrogens. Okay, if we have something like NO2, we have nitrogen there's 1 of, and oxygen there's 2 of. So there's nothing that 1 and 2 are divisible both by, right? That is already the simplest ratio. So we will see sometimes the empirical formula is the same thing as the molecular formula. Because remember, these are all molecular formulas. Okay? So it stays the same because we can't divide 1 by anything, right? It's already the simplest ratio. We have something here like C2H6O2. So 2, 2, and 6 are all divisible by 2. Okay, so in this case, the empirical formula would be C1H3O1, but we know that we don't actually write those ones. We leave it blank, and the reader assumes that they're there. So the simplest ratio would be for every 1 carbon, there's 3 hydrogens and 1 oxygen. So those are the empirical formulas. Remember, they're telling us the simplest ratio in which those elements combine. Okay, so we can actually calculate these experimentally like we saw at the beginning of the slides. So to be able to calculate empirical formula, we actually have to know the percent composition by mass. So the same thing we learned how to calculate last day. Okay. Once we know the percent composition by mass, we can convert the mass into grams, and then from the mass in grams, we can convert it to moles. And we're going to use those mole ratios to figure out the subscripts in the empirical formulas. Okay. So let's take a look at this. So it says this is a type of question you could see. Say you test a small sample and find the compound is 60% magnesium and 40% oxygen. What's the empirical formula? Now, I'm going to give myself a little bit of extra room. So if this is the same question, just written on the next slide. The first thing that we're always going to do in these empirical formula questions is we're going to write that we're going to assume, assuming a 100-gram sample. Now, you could assume a 25-gram or a 15-gram or a 1,000-gram sample, but because we're given these percent compositions in percents, it's easiest just to keep it as a 100-gram sample because we know 60% of 100 is 60, okay? 40% of 100 is 40. So if I assume I have the small sample is actually 100 grams, I would say, well, that means that my mass of magnesium is going to be 60 grams because 60% of 100 is 60 grams. And I'm also going to assume that my mass of oxygen is 40 grams. Okay? Because 40% of 100 grams is 40 grams. Okay? So now that we have our two masses, we can figure out moles, or moles of magnesium. So we would say we know that mass divided by molar mass gives us our moles. So 60 grams divided by The molar mass of magnesium, which if I look that up on the periodic table, is 24.30 grams per mole. That's going to give me the number of moles that I have. So 60 divided by 24.30 is going to be 2.4691 moles. Okay, we'll do the same thing here for oxygen. We would say mass divided by molar mass. So we have 40 grams, and we're going to divide that by the molar mass of oxygen, which is 16 grams per mole. It's 2.5 moles. Okay. So we've assumed 100 grams. We've figured out the moles of each. Okay. Then what we're going to do to figure out the subscripts of our empirical formulas, what you're going to take is your moles of whatever you got, so in this case magnesium, if I want to figure out the subscript of magnesium, and divide it by whatever mole value is your smallest. For example, we got 2.46 and 2.5, so we're going to divide by 2.46, okay, because it's smaller than 2.5. So I'm going to take 2.4691 moles, divide that by 2.4691 moles, and so we're obviously going to get 1. Okay, so our subscript for magnesium is going to be 1 in our empirical formula. Oxygen, if we look, subscript of oxygen, we're going to take our moles of oxygen and divide it by whatever was our smallest mole value. Okay, so we have 2.5 moles, and we're going to divide it by the smallest mole value, which is still 2.4691 moles. What are we going to get? I'm going to get 1.01 mole, 1.01. We know that subscripts though have to be whole numbers, and we can see this is very, very close or equals approximately 1. So what we're going to say is our empirical formula is going to be magnesium with a subscript of 1. So I'm not going to actually write that 1 because we don't write that 1s as subscripts. And oxygen with a little subscript of 1. Okay. These numbers that you're going to get here, what you're going to find is they're going to be really, really close to a whole number. So they're either going to end in, for example, like 0.001 or 0.01 like we saw here, where you can really easily round it, or it's going to be something like 0.998 where you can really easily round it, or you may get something like exactly a half or really close to a half. If you get something like really close to a half, you're going to multiply all of your subscripts by 2. So all 3 of them, let's say, or 2 of them, let's say, by 2 to make them all whole numbers because we can't have a half. But all the answers you're going to get are going to be really close to a whole number like 001 or 999 or really, really close to a half. You're not going to get numbers like a third or a quarter or anything like that. Okay? So it should be pretty obvious when you look at the solutions what your subscript should be. Okay, let's try one more to make sure that we make sense of this. Oh, sorry, I'm going to tell you how you get marked too. On a test or a quiz or exam, how would you get marked? You're actually going to get a mark for writing that statement, assuming a 100-gram sample. So it's really important that you write that down. It is really important, okay? Because the only way you can get the mass is if you explain to the reader that you're assuming a 100-gram sample. You're going to then get a mark for converting your percentages to a mass. You would then get a mark for calculating both of your moles, both of your subscripts, and correctly writing out your empirical formula. So these types of questions would likely be out of 7, maybe out of more if you have more elements. Okay. So let's look at one more example. This says, what's the empirical formula for a compound found to have the percent composition as follows? So 21.6% sodium, 33.3% chlorine, and 45.1% oxygen. So I'm calculating the empirical formula. So the first thing I'm going to write, because I'm going to get marks for this, is assuming a 100-gram sample. Okay. What that means is 21.6% of 100 grams is going to be 21.6 grams for sodium. 33.3% of chlorine is going to be a 33.3 gram sample of chlorine. And the mass of oxygen, 45.1% of 100, is going to be 45.1 grams. Now that we've figured out our masses, we're going to figure out our moles. So moles of sodium is going to be our mass divided by our molar mass. So our mass was 21.6 grams, and we're going to divide that by, if we look on the periodic table, 22.99 grams per mole. Okay, so that's going to give us 0.9395 moles. Chlorine will do the same thing. Moles of chlorine is going to be our mass divided by our molar mass, which is going to be 33.3 grams divided by, if I look it up on the periodic table, 35.45 grams per mole. So that's going to give me 0.9394 moles. And our moles of oxygen is also going to be mass divided by molar mass. So 45.1 grams divided by 16 grams per mole. The 2.8188 moles. Okay. So we've assumed our masses and figured out our 3 moles. So now we have to figure out our subscripts for each of these 3. So the subscript is sodium, is going to be my moles of sodium divided by the moles of whatever is the smallest number. So we have 9395 and 9394 and 2.81. So this one's our smallest. So we're going to divide everything by this number. So this is going to be 0.9395 moles divided by 0.9394 moles. That's going to give me 1.0001. So we know that's equals approximately 1. We're going to use 1 for the subscript of sodium. If we look at our subscript for chlorine, we're going to take our moles of chlorine and divide it by the moles of whatever is the smallest. So it's going to be 0.9394 moles divided by 0.9394 moles, which is going to give me exactly 1, obviously, because they're the same number. And then our subscript of oxygen is going to be our moles of oxygen divided by the moles of whatever is the smallest number. So this is going to be 2.8188 moles divided by 0.9394 moles. That's going to give me 3.0006. Oh wait, did I do that right? Sorry, let me double check. 0.8. I didn't put in a decimal. 188 divided by 0.9394. Oh, no, I was right. So that we can see is really, really close to 3. Okay. So what that means is our empirical formula here is going to be NaClO3. So for every 1 sodium, there's going to be 1 chlorine and 3 oxygens. Okay, this example, you would get a mark for making your assuming statement, your mark for your 3 masses, you would get mark for your 3 mole values being calculated right, and a mark for your 3 subscripts, and then a mark for your formula, empirical formula being right. So this one, because there's 3 elements, would be out of 9. The problem with empirical formula is it doesn't really give us a ton of information about the number of atoms that are actually in a molecule. It gives us the simplest ratio. But for example, if we're only given the empirical formula and we don't know if we have ethene or benzene, those are 2 very different compounds that are used for very different things that have 2 very different sets of physical properties and chemical properties. So it doesn't tell us the actual quantity of the atoms, it just tells us the simplest ratio. So oftentimes we will calculate empirical formula just as a way to later calculate molecular formulas. Okay? So I'm going to show you how we would take molecular formulas and turn them into empirical formulas. So here's what it says. It says, let's say I just calculated that the empirical formula of a substance is found to be CH3. And you are also given the fact that we know the molar mass of the actual compound is 30 grams per mole. What we need to do is we need to figure out how many times this simple ratio, CH3, can actually fit into the overall mass. So here's what we do. Okay. First, what we got to do is you have to figure out the molar mass of the empirical formula. Okay, we need to figure out how much this simple ratio weighs. In this case, it's going to be molar mass of carbon plus 3 times the molar mass of hydrogen. Okay, so if I look that up in the periodic table, 12.01 grams per mole is what carbon weighs, and we're going to have 3 times 1.01 grams per mole, which is the molar mass of hydrogen. So the molar mass of the empirical formula is 15.04 grams per mole. Okay, so that's how much CH3 weighs. That's our simplest ratio. What we need to figure out is how many times does this empirical formula fit into the molecular formula, or essentially what do I have to multiply these numbers by to get the true molecular formula. So you have to figure out something called the multiplier. So how we do that is we're going to take the molar mass of the molecular formula, what was given to us in the question, and divide that by the molar mass of the empirical formula. That's going to tell me how many times the empirical formula fits in the molecular formula. So this was given to me in the questions, 30 grams a mole. And we know this is 15.04 grams a mole. That's going to give us 1.994. Again, this has to be a whole number, so we know 1.994 is very close to about 2. So what that means is to get my empirical formula into a molecular formula, I have to take these subscripts and multiply them each by 2. So even though the empirical formula is CH3, what the actual molecular formula is would be C. Instead of 1, I'm going to multiply that by 2. So it's going to be 2. And H, instead of 3, I'm going to multiply that number by 2, which is 6. The simplest ratio of C2H6 is CH3. Okay, but that's my empirical formula. My true molecular formula is C2H6. Now, if this was a question on a test or a quiz or exam, you get a mark for calculating your molar mass, a mark for calculating your multiplier, and a mark for correctly writing down your molecular formula. Okay, let's try one more. It says a compound with an empirical formula of C2OH4 and a molar mass of 88 grams per mole. What's the molecular formula of this compound? Okay, so this is our empirical formula, and this is the molar mass of the molecular formula. Okay. So first thing we need to do, like we did before, is figure out our molar mass of our empirical formula. So this is going to be the molar mass of carbon times 2 plus the molar mass of oxygen plus the molar mass of hydrogen times 4. So that's going to give me 12.01 grams per mole times 2 plus 16 grams per mole. These numbers are all coming off the periodic table. And 1.01 grams per mole times 4. If I plug that into my calculator, what am I going to get? I'm going to get 44.06 grams per mole. So now that I know how much this weighs, I need to figure out how many times can that fit into the molecular formula. So I need to figure out my multiplier. So to do that, I'm going to take the molar mass of my molecular formula and divide that by the molar mass of my empirical formula. So that means 88 grams per mole needs to be divided by 44.06 grams per mole. That's going to give me 1.997, which we know is pretty close to 2. So I'm going to round that to a whole number. So that means I need to, again, to get my molecular formula, multiply all these numbers by 2. So instead of being C2, it's going to be C4. Instead of being O1, it's going to be O2. Instead of being H4, it's going to be H8. Okay. So my molecular formula is C4O2H8. Again, you would get a mark for calculating your molar mass correctly, if your empirical formula, the multiplier correctly, and your molecular formula correctly. Okay, let's put this all together. This is the last question we're going to go through. This is going to connect our calculation of empirical formula and our calculation of molecular formula. So this question says an unknown compound was found to be 47% potassium, 14.5% carbon, and 38.5% oxygen. If the true molar mass of the compound is 166.22 grams per mole, what's the molecular formula? Well, what we're going to have to do first is calculate our empirical formula because we were given percent composition, and then from that, then we can figure out molecular formula. So we're going to put everything together that we learned today. So first thing I'm going to write, as always, is assuming a 100 gram sample, I will determine my masses. So my mass of potassium is going to be 47 grams. My mass of carbon is going to be 14.5 grams. And my mass of oxygen is going to be 38.5 grams. Okay, so now I can figure out my moles. We know is mass over molar mass. So 47 grams divided by the molar mass of potassium is 39.10 grams per mole. That'll give me 1.2021 moles. I'm keeping a few decimal places here just to make it easier when I'm just calculating the subscripts. I don't want to lose too much of my accuracy. Moles of carbon, same thing, moles divided by molar mass. So this is going to be 14.5 grams divided by 12.01 grams per mole. .5 divided by 12.01 is going to give me 1.2073 moles. And we'll do the same thing for oxygen. It's going to be 38.5 grams divided by 16 grams per mole. So it's going to be 2.4063 moles. Okay, now that I know my 3 moles, I can figure out my subscripts. So my subscript for potassium is going to be my moles of potassium divided by my moles of whatever is the smallest number. So my smallest number, if I look here, 1.2021 is my smallest. I need to divide everything by this number. So 1.2021 moles divided by 1.2021 moles, because the same number is going to give us 1. Our subscript of carbon is going to be moles of carbon divided by moles of whatever is the smallest number. So that'll be 1.2073 moles divided by smallest number, 1.2021 moles. It's going to give me 1.004, which obviously is pretty close to 1, or equals approximately. When you see that little dot, that's saying it's equal to about. And subscript for oxygen is going to be moles of oxygen divided by moles of whatever is the smallest, which will be 2.4063 moles divided by 1.2021 moles. It's going to give us 2.002, which obviously is equal to about 2. So that means our empirical formula for this substance is KCO2. Okay. Now that we know what our empirical formula is, we can use that to determine our molecular formula. We figure out the molar mass of our empirical formula, which is here is going to be the molar mass of potassium plus the molar mass of carbon plus 2 times the molar mass of oxygen. So that's going to be 39.10 grams per mole plus 12.01 grams per mole plus 2 times 16 grams per mole. That will give me 39.1 plus 12.01 plus 2 times 16. It's going to give me 83.11 grams per mole. That's how much the empirical formula weighs, and from that we can figure out our multiplier, which is going to be the molar mass of our molecular formula divided by the molar mass of our empirical formula. So molar mass in the molecular formula was given to us in the question, 166.22 grams per mole. We're going to divide that by 83.11 grams per mole, which will give me exactly 2. So I'm going to take my empirical formula and multiply it by 2. So that means my molecular formula is going to be K2C2O4 because I took 1, 1, and 2 and multiplied it by 2. So this would be a really long answer question on a test or a quiz or exam. It would obviously be out of a lot of marks because we did a lot of steps. So it would be 1 for your assuming statement, 2 for your masses, 3, 4, and 5 for your 3 moles, 6, 7, and 8 for your 3 subscripts, 9 for calculating your empirical formula right, 10 for calculating your molar mass correctly, 11 for calculating your multiplier correct, and 12 for calculating your correct molecular formula. But if you can do this question, it means you've taken away everything that you need to learn from today, because that has all of the new stuff that we learned today in one really long question. Okay, so I have some questions I'd like you to practice. If you look in your textbook, you're looking at 6.9, page 300, question 2 and 6 through 8. So these are what you're going to submit to me on Google Classroom. If you have any questions, check out my office hours or shoot me an email. Also, you can check out the FAQ document to see if another student in class already asked the question. So in the meantime, stay healthy, stay safe, and stay home. Hope to see you guys soon.